Hi, I'm Shreesh Kulkarni, and for my CS5100 Capstone, I reproduced the core experimental claims from Karaman and Frazzoli's 2011 paper on RRT star, a sampling-based motion planning algorithm. This presentation walks through what I implemented, what I found, and whether the paper's claim holds up. So what's the problem? The sampling-based planners like RRT build a tree of random samples to find paths through the obstacle spaces. RRT is fast at finding a path, but the path it finds is suboptimal, jagged, full of unnecessary detours. And here's the key point. More computation doesn't help. Karaman and Frazzoli proved this mathematically. RRT converges to a bad solution with probability 1. The root cause is structural. Each new sample connects to the nearest existing node, and that decision is never revisited. A bad connection made at step 50 stays in the tree forever. RRT star fixes this with two modifications. First, choose parent. Instead of connecting to the nearest node, it looks at all nodes within a shrinking radius and picks the one giving the lowest total cost from the root. Think of it as a local Dijkstra step at every insertion. Second, and this is the most important one, rewire. After adding a new node, it checks whether any nearby nodes can be reached more cheaply through a new node. If they can, it deletes their old parent edge and reconnects them. This is what lets cost improvement propagate backward through the tree. The paper proves this. Uh, the paper proves this makes the algorithm asymptotically optimal. Path cost converges to the true minimum. I set out to test these specific claims. 1. RTT plateaus once it finds a path. More iterations don't help reduce the cost. 2. RTT star improves monotonically. Path cost decreases as the number of iterations n increases. 3. Largest improvement in constrained spaces. RTT star advantage is biggest in narrow passage environments. My scope was 2D Euclidean planning, 50 seeded trials, n from 500 to 5000 across three environments. Here's how I built it. Python, NumPy, SciPy's KD tree for the radius neighbor queries. The KD tree was the main performance risk I identified early on. Without it, RRT star degrades to O of n per iteration and actually becomes slower than RRT, which would defeat the purpose. The rewiring radius follows theorem 38 from the paper exactly. I added a 10% safety margin on the gamma constant because the free space volume has to be estimated, and I floored the radius at the step size to prevent collapse at small n. Now here's the most important implementation detail. After every rewire, we need to update the cost of every descendant of the reparented node. I do this with BFS traversal. The paper doesn't really emphasize this, but without it, the stored costs get out of sync and all subsequent rewire decisions are silently wrong. This was the hardest bug to find. Let me show you quickly in the code. Here's the function. After a rewire, it walks through every child and recomputes cost as parent cost plus the edge distance. Simple BFS, but if you skip it, the algorithm looks like it works but produces wrong cost values. Three environments, increasing difficulty. Environment A is simple, one big obstacle, forces a basic detour. Environment B is a narrow passage, two tall walls with one unit gap. Random samples only hit the gap about 10% of the time, so this is the hardest one of the both algorithms. Environment C is a maze with 6 scattered obstacles that force winding paths. The full experiment is 50 seeded trials per condition. 5 values of n from 500 to 5000. That's 1500 total runs. Here's environment A at n is equal to 2000. Single run. Left is RRT, sparse tree, 111 nodes, jagged path with cost of 14.81. Right is RRT star, dense tree filling the entire free space, 1976 nodes. Smooth path hugging the obstacles corner at cost 11.99. That's a 19% improvement in one run. Environment B, the narrow passage. This is the most visually striking comparison. RRT finds the gap but enters a bad angle. Cost is 9.5. RRT star threads almost a straight line through the gap. The cost is 7.53, 21% shorter. And look at the tree density. RRT star has explored the entire free space on both sides of the wall. Environment C, the maze. RRT wanders through the obstacle field. Cost is 16.5. RRT star finds a cheaper route at 13.74, which is 17% shorter. You can see how the RRT star tree fills every corridor. Before I walk through the convergence curves, let me run one live demo. Switching back to the terminal, I will be running this experiment for environment A with n is equal to 2000 and seed as 42. We can see that the output was stored in a figure. Let us open it up. RRT 111 nodes and the cost is 14.81. RRT star 1976 nodes and the cost is 11.99. Matches what we saw in the figures. Going back to the presentation, the convergence curves, this is the key result. ENVA, the blue dashed line, is RRT, completely flat at 15.09, regardless of the n. The orange line is RRT star, starting at 12.27 and dropping to 11.97. Notice how tight the RRT star's shaded band is compared to RRT. That's the variance difference. Moving forward, environment B, the narrow passage. Same flat line for RRT. RRT star drops from 7.79 to 7.59. The gap between the two algorithms is the widest here. 24%, 24.5% at n is equal to 5000. This confirms the paper's prediction that constrained environments benefit most from rewiring because RRT star keeps straightening the passage crossing segment with each new sample. Environment C, the maze. RRT star is still improving at n is equal to 5000. It hasn't fully converged yet. Cost drops from 14.02 to 13.37. A 4.7 internal reduction. With more iterations, this would keep going. Putting it all together, at n is equal to 5000 across 50 trials, RRT star produces paths that are 20 to 25% shorter than RRT. The variance is 10 to 30 times lower. RRT star doesn't just find better paths, it finds them reliably. The gap to the theoretical optimum is 5 to 6%, and that would continue shrinking with more iterations. Success rate is 100% everywhere at n is equal to 1000 or higher. Looking at the table, environment B shows the largest improvement at 24.5%. For environment A to 24.7%, environment C at 21.6%, and the RRT star standard deviations are tiny, 0.03, zero 0.06, and 0.08. Compare that to RRT, where it's 0.83 to 1.01. On runtime, RRT star at n is equal to 5000 takes about 3 seconds per trial. RRT takes 3 milliseconds. But that's misleading. RRT only runs 90 to 190 iterations before stopping. The per sample cost of RRT star is about zero point 0.6 milliseconds, dominated by KD tree rebuilds. The biggest tree production challenge was the cost propagation issue I mentioned. My first implementation only updated the direct rewire node, not its descendants. The tree looked correct, the paths appeared to improve, but the internal cost values were wrong. It took a while to catch because the visual output was misleading. The free space volume estimation was also tricky. The radius formula depends on knowing the exact absolute free space, which you have to estimate. I used 85% of the map area minus obstacle area with a 10% safety margin, which worked, but if you are off by a factor of 2 in either direction, the result degrade visibly. On the limitation side, this is 2D only. The paper's theory generalizes to higher dimensions, but it didn't test that. N is equal to 5000 is modest for asymptotic claims, though it's enough to see the quantitative behavior clearly, and I didn't implement PRM star for comparison. To wrap up all three claims, reproduce cleanly. RRT plateaus the mean cost is literally identical at every value of n across 50 trials. RRT star improves monotonically in every environment, and the largest improvement is in the narrow passage, exactly as the paper predicts. The reproducibility verdict is partially reproducible. The core algorithm and theoretical claims are fully specified and they hold up completely. But several implementation details, cost propagation, free space volume estimation, KD tree integration, are left underspecified. Someone implementing RRT star for the first time from the paper alone would almost certainly hit the cost propagation bug. The claims themselves, though, are solid. Thank you and have a nice day.